So screen is visible to everyone.
Yes, ma'am.
Okay. So everyone, welcome to the course. Welcome to the course Basics of Materials Engineering. So in week 1 we'll be studying about introduction and crystal structure. So this course is taught by Professor Ratna Kumar from Department of Mechanical Engineering, IIT Madras. I am your TA Alka Jangid from IIT Kanpur. So firstly we'll be going through some sample assignment questions which are similar to your assignment. Then we'll be going through some notes which will be helping you in solving the assignment that you are given in this week. Okay, so firstly I'll start. First question is the effective number of lattice points in the unit cell of simple cubic, body centered cubic and face centered cubic space lattices respectively are. So your options are 122, 124, 234 and 244. Now can anyone, if you know the answer, please write in the chat. So the answer will be 124. And you can solve this by simply taking, in case of simple cubic, as you know there will be atoms at the corner of the unit cell. So one cube is shared by 8 other unit cells. So 1/8 atom will be inside this cube and it has 8 corners. So 1/8 times the 1/8 times the 8, so it will be 1 atom per unit cell in case of simple cubic. And in case of body centered cubic, you will be having 1 atom at the body center and 8 atoms at the corners, similar to simple cubic. So there will be 1 extra atom, so it will be having 2 atoms per unit cell. In case of face centered cubic, there will be atoms at the face centers. So a cube will be having 6 faces. So we'll be multiplying 6 by half, because if one atom is at the face of the at the face center, then it will be shared by 2 cubes. So it will be having 4 atoms per unit cell. Now second question is the coordination number for FCC crystal structure is. Your options are 4, 8, 12 and 16. So what can be the answer? So answer will be 12. In case of FCC and HCP, both will be having 12 coordination number. What is coordination number? It is the number that can be defined as the nearest neighbors in the crystal structure lattice. For example, in this is along the particular direction. So in this, for this atom, it is surrounded by 6 atoms, where 6 neighbors, and these 3 atoms and these 3 atoms, these will be having again similar distance. So these are 12 atoms that are surrounding this atom. So these will be having 12 coordination numbers, similar to FCC. And for BCC, in case of BCC, coordination number is 8. So in that case, you can imagine the body center atom, and it will be having nearest atoms will be at the corners. So that will be having 8, and in case of simple cubic, it will be having 6 coordination number. Now a family of Miller direction is always represented as. Now these are the options. Any new participants? Okay. Okay. So in case of family of Miller direction is always represented as, so your options are small bracket, curly bracket, triangular bracket, or this square bracket. So your answer will be triangular bracket. So these are various conventions for denoting the direction, family of direction. In case of direction, you have square bracket, and in case of family of direction, you'll be using triangular brackets. In case of a plane, you'll be denoting it as small bracket, and in case of family of planes, it is denoted as curly brackets. And HKL are integers which don't have any common factors between them. So these will be whole numbers. Now, which one of the following pairs of the axis lengths A, B, C and interaxial angles alpha, beta, gamma represents the tetragonal system? Now, in case of, it is similar to a cubic system, but just one direction will be having, won't be equal. So it will be having all angles 90 degree, and if all these are not equal, then it will be orthorhombic. So this will be the answer, D. A equal to B equal not to C, and alpha, beta, gamma are all 90 degree. Now these other systems are also given here. So one of the example of tetragonal system is Martensite. So it has BCT structure. So at the body center there will be one atom. Now in case of cubic, these all will be equal, interaxial angles as well as axis. In case of hexagonal, it will be in this form. So A equal to B equal not to C, and in case of interaxial angles, you will be having alpha equal to beta equal to 90 degree and gamma will be 120 degree. In case of tetragonal, okay, we have new participant, admit, okay. In case of tetragonal, as told earlier, A equal to B equal not to C. So only one direction, C won't be equal. In case of orthorhombic, these axes won't be equal. All axes won't be equal. And in case of rhombohedral, one angle won't be equal. These angles won't be equal to 90, any angle. In case of monoclinic, you'll be having no direction will be equal, and all the angles alpha and gamma will be 90 and beta won't be equal. In case of triclinic, it shows least symmetry. So nothing is equal in this case. Now for the next question, a crystal system with three two-fold axis of symmetry is known as. Your options are orthorhombic, cubic, tetragonal and monoclinic. Your answer will be orthorhombic. So these are various systems and their required symmetry level. So in case of orthorhombic system, it has two-fold axis of symmetry. In case of cubic, three four-fold axis symmetry will be there. So cubic is most symmetric system and triclinic is least. It doesn't have any symmetry. In case of tetragonal, it will be having one four-fold axis. In case of orthorhombic, three two-fold axis, which is the answer. In case of hexagonal, as the name you can remember, hexa, so it has one six-fold axis. In case of rhombohedral or trigonal, it has one three-fold symmetry. And in case of monoclinic, it has one two-fold axis symmetry. Next question is, the ideal C by A ratio for HCP crystal structure is. So answer will be 1.63. So this you can by using these angles, triangle and Pythagoras theorem, you can calculate this angle by using this particular triangle. So here for AXC triangle, you can calculate and put the values in terms of C and A. So C is your vertical axis. In case of this, so this is your C and A will be this direction. So C by A ratio you have to calculate. So for ideal system, it will be 1.63. Now 7th question is a regular solid formed by 5 regular triangles meeting at one vertex is called. Your options are dodecahedron, icosahedron and octahedron, or such a solid is not possible. So your answer will be, in case of 5 regular triangles, it will be icosahedron. And these are various your platonic solids. So in this case, various triangles will be meeting at vertices. So in this case, if three triangles are meeting at a vertex, then there will be tetrahedron. If 4 are meeting, then it will be octahedron. If 5 are meeting, then it is icosahedron. This is, and in case of a square hexahedron, it will be three cubes that will be meeting at a vertex. In case of pentagon, it will be dodecahedron. Now 8th question is, if the electronegativity values of titanium and oxygen are 1.5 and 3.4 respectively, the percentage ionic character of titania compound is. You have to tell the percentage of ionic character. Now for ionic character, you have simple formula. It is 1 minus exponential minus 0.25 times the difference in electronegativity square, then bracket and times the, for the percentage you have to multiply it with 100. Now difference you can calculate by taking higher electronegativity minus lower one. So 3.4 minus 1.5, which will be 1.9. So you'll be keeping 1.9 here, its square. Then you can calculate it to be 60%. So your answer will be in this range, around 60. 9th question is, a common crystal structure for ceramic material is. Your options are FCC, BCC, HCP or perovskite. Okay, so in case of ceramics, you have some complex structures compared to, they won't be in form of FCC, BCC, HCP, they will be for metals. In case of for ceramics, they solidify in complex structures. One of those is perovskite. So this is your structure which looks like. Perovskite is any material with a crystal structure following the formula AbX3, which was first discovered as the mineral called perovskite, and which consists of calcium titanate oxide, CaTiO3. Now these other structures, they are for metals. Now 10th question is, which material class is a good conductor of heat and electricity? So your options are ceramics, metals, polymers and aerogels. Now except metals, all these materials are insulators both thermally and electrically. In case of metals, they have valence electrons around 1 to 3, so they are loosely bound to the your nucleus, so they can be easily so these electrons, they make them excellent conductors of heat and electricity. So some of the examples are copper, aluminium, titanium, gold, silver, iron and nickel. Now I'll be going through some lecture notes. So firstly, the history and evolution of materials. So firstly we'll be going through what materials are, and then we'll be going through crystal structures. So firstly, materials are rooted in our culture and have influence over virtually every segment of our daily lives. For example, in case of transportation, your railways and aeroplanes, these all require some materials. So as the materials keep on showing some, there will be some research in materials, then these, in case of transportation also, there will be some innovations, some evolutions, they'll be there. In case of housing also, we require some ceramics related materials, some metal waste materials. In case of clothing, you require some polymers. In case of communication, in case of recreation activities, all these require materials. Now, early civilizations have been designated by materials development. For example, Stone Age, Bronze Age, Iron Age. So, we'll be going through these ages. So, in case of Stone Age, the term was coined in late 19th century by the Danish scholar Christian Thomson, and it roughly extended between 15,000 to 2000 BC, and this is characterized by creation and use of stone tools. So these were used. Now wood, bones and other materials were also used as tools, but they had shorter lifetime. Other is Bronze Age. It roughly extend between 3500 to 500 BC, and in this there was beginning of metal working. So copper was mixed with tin, which led to increase in strength, and it was used to create a new alloy, bronze. It was stronger than the other two metals individually. It was used for tools, weapons, and some for some decorations. Now other age is Iron Age, which is latest in these three age system. After that there is also Carbon Age, Silicon Age, but we are talking here about Iron Age. The Iron Age began about 3000 years ago and it continues today. The use of iron and steel has changed drastically human development. For example, it has improved the modes of transportation for automobiles, railways, and aeroplanes. And in case of iron pillar, it is a solid shaft of wrought iron with high phosphorus content, about 7 meter tall, 0.4 meter diameter, weighing over 6000 kg. Now this pillar hasn't shown any rusting, which is because of formation of a even layer of crystalline iron hydrogen phosphate hydrate, which serves to protect it from the effects of local Delhi climate. Okay, so for now, the various definitions for material science and materials engineering. Now there is difference between these terms. In case of material science, it deals with the structure and property correlation. So as the structure of a material changes, its properties also changes. So it deals with this. In while materials engineering deals with design and engineer the structure of a material for a specific application, and this also relies on material science. Now structure is the arrangement of internal components and structure is scale dependent. For example, it can be subatomic, so there will be how electrons are there in their shells, so that will affect your electrical or magnetic properties. Atomic arrangement, so how atoms are situated in your crystal structure, so that will affect your for example plastic deformation. It can be microscopic, so at a microscopic level there can be formation of some precipitates, there can be some impurities. so that will be microscopic. And macroscopic can be presence of, for example, pores or cracks. Property is characteristic response under the action of external stimulus. So these stimulus can be mechanical, electrical, thermal, magnetic and optical. Now based on these there will be the properties of materials. Now this is the tetrahedron of material science. So in this case the other two options are important aspects are also processing and performance. So the how materials are processed by various for example casting or metal working, these all also affect the properties of materials. So these all aspects are interrelated to each other. Now material classification. So engineering materials are classified as metals, mainly ceramics, polymers and composites. They can also be non-metals separately. So in case of metals, there will be ferrous and non-ferrous metals. Ferrous will be consisting of iron. So there will be cast irons, there will be steels or some other iron alloys. In case of non-ferrous, there will be copper, aluminium, titanium and all remaining metals and their alloys, there will be non-ferrous. In case of non-metals, there will be gases such as hydrogen, helium, nitrogen, oxygen. They can be liquid such as bromine. They can be solids such as carbon, phosphorus, sulfur, selenium, iodine. For ceramics, these are the compounds which have very high melting point. These are the compounds having very high melting point. Now others are polymers which will be having wool, silk. These two are examples of natural polymers. And polythene, PVC, nylon, bakelite, these are man-made polymers. Composites are the combination of these three main classes. So it can be wood, concrete, these are again found naturally. Fiberglass, CFRP, carbon fiber reinforced plastics, and these are man-made glass fiber reinforced plastics. Now firstly we'll be going through metals. So metals are characterized by the following properties. So these, in case of physical properties, they are good electrical and heat conductors, and they show good malleability, which is the ability of material to be beaten into thin sheets. These can be ductile, so they can be stressed into thin wires, and they possess metallic luster. So the luster can be seen in these all metals. Now these are solid at room temperature except mercury. And chemical properties, so these have 1 to 3 electrons in the outer shell, so these can lose their valence electrons easily. So and also they form oxides that are basic. For example, iron oxide, it will act as a basic. So these are good reducing agents because they lose electrons easily and they have lower electronegativity. So they have tendency to attract electrons. This is the definition of electronegativity. Tendency to attract electrons. Now non-metals are characterized by following properties. So firstly, physical properties, they are opposite of metals mostly. So they have poor conductivity of heat and electricity. They are brittle while they were ductile, and if they are in solid form they will be brittle and they do not possess metallic luster. Some are transparent when they are in thin sheet, and they are solids and liquids or gases at room temperatures. Now chemical properties, they usually have 4 to 8 electrons in their outer shell, so they will be attracting electrons. So they want to gain or share electrons easily, valence electrons. They form oxides that are acidic and they are good oxidizing agents. They have higher electronegativity. Now other class is ceramics. These are materials which are made of inorganic materials from compounds of metal and non-metal. They are formed by the action of heat and subsequent cooling. They are brittle in nature and good insulator of heat and electricity. And they show good compressive strength while poor tensile strength. Their applications are in making roof tiles and bearings. Bearings are made using silicon nitride, silicon carbide, and some ceramics coated turbine plates and pottery. These are some applications of ceramics. Polymers is other class. So these are just large molecules composed of many repeated subunits. These are organic in nature, so there will be carbon, hydrogen, nitrogen, sulfur, these all elements present in these. So one is natural polymers. So in this case, for example, shellac, amber, wool, silk and natural rubber, these are found naturally. In case of synthetic, there is synthetic rubber, bakelite, neoprene, nylon, polystyrene, polyethylene, PVC, these are synthetic. Composites is made when two or more constituent materials with significantly different properties, which after combination produces a material with characteristics different from the individual components. Now the individual components remain separate, so there will be some physical boundary between them and they'll be distinct within the finished structure. So for example, these fibers and this is the matrix. Matrix will be the continuous your continuous material that will be there. So these, if it is polymer, then it will be called polymer matrix composite, PMC, or if it is metal matrix, then it will be MMC, or it can be ceramic matrix composite, so your ceramic will be matrix. And the reinforcement will be, it can be fiber, it can be particles, so that it will be inside this, so it will be combined called composite. Now there are smart materials also, so these can change their physical properties in a specific manner in response to specific stimulus input. So these are commonly used smart materials such as piezoelectric materials. Someone has joined. Okay, so first is piezoelectric material. In this case, it will be generating some electric charge in response to the applied mechanical stress, or there can be some mechanical strain developed when there will be application of some electric voltage. In case of magnetostrictive materials, they change their dimension of ferromagnetic material in a magnetic field or vice versa. So there can be magnetic field and there will be some strain generated inside material. Phase transition dependent. So these are the shape memory alloys. So in this case, they remember their original shape and after being deformed, they return to their original shape when they are heated. Electromagnetorheological materials, so these change their viscosity in response to electric or magnetic field. Other class is biomaterials. So these are the substances excluding food and drugs are introduced inside living body with the aim of improving or replacing a diseased or damaged lost tissue or a whole organ. Some of the examples are joint replacement, bone plates, bone cement, some dental implants, heart valves, or contact lenses. These all are biomaterials. So these materials can be either metals, polymers or ceramics. So these are some examples. For example, in case of metals, cobalt chromium alloy, stainless steel, gold, titanium alloys, vitalium, amalgams, shape memory alloys, nitinol, copper zinc aluminium alloy. These all are biomaterials. Now they are used in orthopedics, dentistry, stent, etc. In case of polymers, silicons, polyethylene, polyurethanes, polymethyl methacrylate, PMMA, which used as bone cement to fill space between bone and implant. These polymers, they are used as orthopedics, artificial tendons and vascular grafts, facial and soft tissue reconstruction. In case of ceramics, alumina, calcium phosphate. This calcium phosphate is used for bone grafting, synthetic hydroxyapatite, which is used to promote bone and growth, pyrolytic carbon, which is used as lining on blood contacting prosthesis. Now other category of these materials is aerogels. Now these are materials with around 90 to 98% porosity. Now they are produced by extracting the liquid component of a gel through supercritical drying. The air molecules are trapped inside the gel and they act as insulator. Now its heat conductivity is close to zero, so they are used as insulators or noise barrier. Now some of the application is in capturing space dust from comets and insulating material in space suits of NASA astronauts since 1960s. Some potential applications can be in making thermal barriers for extreme cold region, clothes such as for Siachen, which requires around only 500 gram of gel to coat a jacket. Thermal insulators for cryogenic fuel tanks of rockets, acoustic insulators, buildings and pipeline insulation. Superconductors, it can be an element, intermetallic alloy or compound that will conduct electricity without resistance below a characteristic critical temperature. It is costly due to cryogenic requirements, so you need to maintain a temperature below 0 degrees Celsius, so it is costly. Now examples are mercury, lanthanum, barium, copper oxide, niobium tin, yttrium, barium, copper oxide, etc. Other is CNT. Now carbon nanotubes. It is used as reinforcement in many materials. Now it was discovered in 1991. It is composed of carbon atoms linked in hexagonal shapes with which carbon atom covalently bonded to 3 other carbon atoms. So carbon nanotubes, these have diameter is as small as 1 nanometer and lengths up to several centimeters. These nanotubes are the strongest and stiffest material yet discovered, and they have very good electrical conductivity as well, and in terms of tensile strength and elastic modulus respectively. So these are also very high, so they are strongest and stiffest materials. CNTs are at least 100 times stronger than steel but only 1/6 as heavy. Extremely high thermal conductivity, so around 10 times of copper, and electrical conductivity is 100 times of the copper. Now combining carbon nanotubes with other materials into composites can be used to reinforce and building lightweight structures. Now various questions are in your assignment are related to platonic solids. So these are any of the 5 geometric solids whose faces are all identical. So these will be either triangles or pentagons, or these faces can be either squares. So these are regular polygons meeting at a same 3-dimensional angles. Now these are also known as 5 regular polyhedra. They consist of the tetrahedron or pyramid So these are cube, octahedron, dodecahedron and icosahedron and tetrahedron. These are 5 platonic solids. Now these are the number of faces that they have. Now for the periodic table, so in case of periodic table, when you go along the columns, you see that they have similar number of valence electrons. For example, in this line, so these all elements, they show similar type of behavior. So they have valence structure similar. So, and when we move to the right side, then electronegativity will increase because they are gaining more number of electrons. So they readily acquire electrons to become negative ions, and fluorine is most electronegative. While we go in this side, at the left side, then they show electropositivity increase. So they readily give up electrons to become positive ions. Now cesium is most electropositive. Now understanding the origin of material properties, it requires study at atomic level. So these are the spring type of bonds, they are shown bonds. Now in case of interatomic bonds, there will be hold atoms. This bonds will be holding these atoms together and they act like springs by linking one atom to other in the solid state. Atomic packing is, this signifies the way in which atoms are packed together. So atomic packing will be related to your crystal structure. Now number of springs per unit area and angle at which they are pulled, it will decide how your crystal structure will look like. Now crystallography. Now this is the study of atomic and molecular structure. So the study of crystal geometry helps to understand how the atoms in a material are arranged in order to interpret the relationship between atomic structure and properties of these materials. For example, mechanical properties. So how the atoms are arranged, how it will affect its mechanical properties, or electrical properties, magnetic properties, optical properties and metallurgical properties. Now the common technique to know what the crystal what type of crystal structure is a material is having, we use X-ray diffraction technique. Now this is the classification of solid materials. So they can be either crystalline, they can be either polycrystalline, or they can be amorphous. Now first is crystalline solids. So in this case, there will be a regularity of the atomic or ionic arrangement. So they will be having long range order. So long range structure exists in which atoms are arranged into unit cells, and unit cells repeat in a regular orderly pattern following a lattice. So this will be forming a 3D lattice. Each atom is bonded to its nearest neighbor, and some of the properties depend on the crystal structures. For example, if there is a crystalline structure, they will be having a directional properties. So they show anisotropic behavior. So for example, in this direction and this direction, they will be having different strength or different tensile strength, or these type of properties will be different. Sharp melting point. So these have different melting points, and all metals, many ceramics and some polymers form crystalline structures. Polymers also have some crystalline structures in between them, not entirely crystalline, but some part of it will be crystalline. And examples are gold, silver, aluminium, etc. Other categories, polycrystalline solids. So these are made up of an aggregate of many small single crystals, also called crystallites or grains. Now across grain boundary, the orientation of the crystal changes. Now the grains are usually 100 nanometer to 100 microns in diameter. Polycrystalline materials have high degree of order over many atomic or molecular dimensions. So polycrystals with grains that are less than 100 nanometer in diameter are called nanocrystalline. So the size of this grain, if it is lesser than 100 nanometer, then this material will be called nanocrystalline. Now most engineering materials are polycrystalline. For example, steels or uh, copper, whatever you see around you, these all are polycrystalline. Properties may or may not vary with direction. So these may be either anisotropic or these may be isotropic. So for example, if grains are textured due to rolling, so if we perform some mechanical thermomechanical treatments, someone else has joined. Okay, so if grains are textured due to rolling, then it will be anisotropic, and if grains are random, then it will be showing isotropic properties. So in all directions, your elastic modulus or your tensile strength will be equal. This is what your polycrystalline solid looks like. So these are the grains and these boundaries are grain boundaries. Single crystal, so it will be having only one grain and there won't be any grain boundaries. It is found by uniform cooling of liquid material. It has high degree of order throughout the entire volume of the material. Now it is useful for applications where grain boundaries are harmful. For example, high temperature deformation or creep resistance. So if we require high creep resistance is at higher temperatures your structure should be stable. So for that you require less number of grain boundaries. So single crystal turbine blades are used, which are nickel based superalloys gas turbine blades. These withstand creep at very high temperatures due to lack of grain boundaries. And also in case of diamond, they are not. This is also a example of single crystal. In case of semiconductors, for proper doping, we also require single crystals. Other category is amorphous solids. So in these, the atoms or molecules are arranged in a irregular manner. So there won't be any long range order. So no periodic packing will be there and no directional properties will be there. So these show isotropic properties and these occur for complex structures. So for example, if there are more than 4 to 5 metal elements are there, for example in case of high entropy alloys, or if in that case it is more likely to show amorphous nature. And if there is rapid cooling of a single metal as well, then it might show formation of bulk metallic glasses, which is again amorphous structure. Some of the common examples are glass, plastic, rubber, etc. This is the structure of silica. So here silica also shows amorphous nature. Now unit cell, it is the smallest block or geometrical figure from which the crystal is built up by repetition in 3 dimensions. So the fundamental grouping of particles which are repeating entities. So this single unit cell, so if we repeat it in multiple directions, then it will be giving your entire crystal. So this is called unit cell. So unit cell is a basic structural unit or building block of the crystal structure. A crystalline solid can be constructed from a unit cell plus translation operators. So these translation operators will be in various directions. So for example, if in x-axis we'll be getting this one dimensional crystal, and if we are in y direction as well, if we are translating it, then it is 2D crystal. For 3D we have to do z direction as well. Now crystal systems. So crystal system is made by firstly lattice and basis. These are two entities. So in case of lattice, it is array of points in space. So it is a mathematical representation. It doesn't have any physical entity to it. So array of points in space in which every point has an identical environment. For example, this atom has nine this atom has multiple atoms surrounding to it, which is similar for this atom as well. So single atom or basis is your single atom or group of atoms identical in composition and orientation in space. So it can be a single element or it can be a molecule. So it will be repeating at these points. So combining both of these, it will give you crystal structure. Now these are various crystal systems that I told earlier. So cubic, hexagonal, tetragonal, trigonal, orthorhombic, monoclinic, triclinic. These are your crystal systems. Now these are crystal structures. So first is simple cubic. In this case, a unit cell consists of 8 corner atoms, and all these corner atoms, they contribute only one effective atom for the lattice. Now number of atoms per unit cell. So as we calculated earlier, in this case you will be having 8 atoms at the corners, 8 corners, and one atom is shared only 1/8 in this cube. So it will be 1 atom per unit cell. Now for calculating packing fraction, you have to firstly consider the volume of the atoms divided by total volume of the unit. So unit has the lattice parameter is A. So 8 cube will be its volume, and the effective number of atoms is 1 times the volume of one sphere. So we are considering atom as sphere. So 4/3 pi r cube. R is your radius of atom. Now by calculating this, we get that 52.4% will be your packing factor. Now coordination number is the number of atoms immediately surrounding a central atom in a crystal. So coordination number, as I told earlier, for simple cubic, we can consider this atom. So it has 6 atoms, which will be 2 will be up and down and 4 will be at this plane. So it will be having 6 coordination number, and the example of simple cubic is polonium, and it is rare due to poor packing. Now other crystal structure is body centered cubic. In this case, number of atoms per unit cell are 2. So at the body center there will be one atom that won't be shared with other cubes. So it will be having 2 atoms per unit cell. So in this case, when you will be calculating, you will be multiplying this by 2, and the relation of R and A, in previous case you had A equal to 2R. In this case you have A equal to 4/√3R. So this you can, by simple trigonometry, you can get these relations, and the packing fraction will be 0.68 in this case. So it is relatively densely packed compared to simple cubic. In case of BCC structure, it has 8 corner atoms and 1 body center atom, and the coordination number is 8. So this atom has these all 8 corner atoms as neighbors. Now examples are chromium, iron, molybdenum, potassium, sodium, tantalum, vanadium, etc. Iron at the lower temperature and at very high temperature it shows BCC, but after certain temperature around 912 it shows FCC structure. Now number of atoms per unit cell in case of FCC structure, it will be having atoms at the face centers. So each face center has 8 FCC has 8 corner atoms, so one atom will be from there, and your will be having 6 atoms from face center, so they are shared by 2 cubes, so 3 atoms will be from there, so 4 atoms, and the relation will be A equal to 4 by root 2 R, and the packing fraction will be 7.74. Now coordination number is 12, and examples are aluminium, copper, gold, silver, lead, nickel and platinum. These all are very ductile in nature for all FCC materials. Now other is hexagonal centered cubic. In this case, number of atoms per unit cell is 6. So these 3 atoms inside this, these are not shared, so these 3 atoms will be there inside this, and 1 atom will be from this outside circle. From this circle there will be 1 atom, 1 contribution will be from this outside circle, so 2 atoms are from there, 3 atoms are from there, 1 atom will be here at the center, which is shared by 2 units, so 1 at half, so 1 atom, so thus there will be 6 atoms. And packing fraction you can calculate, it will be similar to FCC, so it is also close packed structure. It has 0.74 packing fraction, and its stacking sequence is AB. So as you can see, this continues here, so AB, like that it will be having stacking sequence. Someone has joined. Okay, so coordination number is 12, and examples are magnesium, cobalt, zirconium, titanium, zinc, cadmium, beryllium. At room temperature, most of these are little bit brittle. They are less ductile compared to FCC. Now other topic is Miller indices. So Miller indices are the designations of planes and direction in the unit cell. So the number of indices will match with the dimension of the lattice or the crystal. So for example, in case of 3D, the unit cell has 3 indices, H, K, L. Now HKL represents a point, and here we won't be using comma. So comma is used in case when we used some coordination points. Now these are the symbols that we use. For example, half moon bracket or this small bracket is used for individual plane. Family of planes is used for curly brackets, and square bracket is used for individual direction. Triangular bracket is used for family of directions. So these all directions are family. So 100 is also if it is written in this case 010, 001, all these will be considered along with this. Now how to find the Miller indices of a plane? So firstly we'll be going through for Miller indices of a plane. So in this case, first you have to choose an origin. So choose origin such that plane does not touch the origin, and plane is closest to the origin. So we choose origin such that it is close to the plane. Now we mark the intercepts from the chosen origin. So in this case, where it is here, it is intercepting at A, B, C. So it can have, like for example, it is 1 unit, it is 2 unit, like that. So it will be, then we take reciprocals of that. For example, if 1 by 1, 1 by 1 or 1 by 1, if it is cutting at 1 on all those cases, then we'll be having these intercepts. Then you have to modify the reciprocal. So to reduce multiples, if it is for example 2, 2, 2, then we have to divide it with 2, all of those, then it will be 1, 1, 1, like that. And if it is in fraction, for example it is 1/3, 1/6, like that, then you have to multiply it with something. so that all these become a integer. Now we put a bar when there is negative integer, so there will be 1 bar in case of -1. So we place round bracket around indices. If it is round bracket, then it is a single plane. In case of direction, you have to create new origin o dash at tel. So you can shift the origin as well for simplicity. So we label o dash and then again you label your axes. So x dash, y dash, z dash. Now we find the coordinates from the tail at o dash to the head of the direction. Now we reduce multiples, we eliminate the fractions and use bar for negative, similar to previous one. So you have to place square bracket around the integer. For example, here you are going from this side, so to reach this point, how much you have to walk in x direction, how much you have to walk in the y direction, how much you have to walk in z direction. So here if I am walking in x direction, so I am walking +1 in x direction. In y direction I am walking -1 direction, -1 of y. In z direction I am walking in +1 in z direction. So 1 bar, 1 will be its Miller indices. Now that's all from the notes. Now I'll be repeating the questions. I'll be going through questions once more. So firstly, first question was the effective number of lattice points. Okay, so first question was effective number of lattice points. So we calculated it multiple times. So for example, simple cubic, body centered, face center, you have to just remember like where will your atoms will be situated and how many units it is sharing it with. So in case of simple cubic, there are 8 atoms at the corners and they are shared with 8 other units. So there will be 1 atom per unit cell. In case of BCC, you will be having 1 extra atom at the body center. So there will be 2 atoms per unit cell. In case of FCC, you have atoms at the face centers. And this face is shared with 2 cubes. So it will be half times the 6. So it will be 4 atoms per unit cell. In case of HCP, you will be having 6 atoms per unit cell. Now the coordination number for FCC crystal structure is, your options are 4, 8, 12, 16. Now this is what your HCP will look like. So in this case, you have to just check how many neighbors, closest neighbors it has. That will be its coordination number. So for this atom, it has 6 adjacent atoms and 3 atoms up and 3 at bottom. So these will be 12 atoms for both HCP and FCC. A family of Miller direction is always represented as triangular brackets. So these are conventions for Miller indices, family of planes and family of directions, these all. And fourth question is, which one of the following pairs of axis length ABC and interaxial angles alpha, beta, gamma represents the tetragonal system? Your options are these, and in case of tetragonal, you will be having just one direction different than the A and B. A crystal system with 3 two-fold axes of symmetry is known as, option will be orthorhombic. So these are various symmetries for various systems. So for orthorhombic, you will be having 3 two-fold axes. Ideal C by A ratio for HCP, it is 1.63. You can remember it or you can also learn to solve it. So it is simple trigonometry. You can use that and you can simply find it will be √8/3, which will be 1.63. Question 7 is a regular solid formed by 5 regular triangles meeting at one vertex is called. Options are dodecahedron, icosahedron, octahedron, or such a solid is not possible. So answer will be icosahedron. In this case, you will be having 5 of triangles meeting at one vertex. In case of octahedron, you will have 4 of such triangles. In case of tetrahedron, 3 triangles will be meeting at one vertex. So these all you can easily imagine and answer. Question 8. If the electronegativity values of titanium and oxygen are given, what will be the percentage ionic character of titanium oxide compound? Now the formula is 1 minus exponential minus 0.25 times the delta electronegativity times the square. Now you have to just calculate this and put in the formula, and you will be getting around 60% of the ionic character. A common crystal structure for ceramic materials is FCC, BCC, HCP, or perovskite. Answer will be perovskite. Now this is a complex structure for ceramics, so it is of the form of AbX3. BCC, FCC, HCP, these are some common examples for metal crystal structures. 10th question is, which material class is good conductor of heat and electricity? Answer will be metals. Others are insulators of heat and electricity. Now metals, because they have 1, 2, 3 electrons in outer shell which are loosely bound, so they can lose these and easily get and form a electron cloud, which will make them electrically conductive. Now that's all. Now let me know if you have any queries. If you have any queries, you can ask. Yes. You have to unmute yourself. I can't hear you.
Hello.
Yes, sir.
My name is Shivanand Poojar.
Yes.
Lecturer from Government Polytechnic, Hubli, Karnataka.
Okay.
Can you share this particular presentation?
Yes, I'll be sharing it.
You are sharing. Okay. Thank you.
This presentation and the video will also be shared on YouTube. So NPTEL will tell you where you can access this.
Okay.
They will be giving you the link for the Google Drive where these all presentations will be saved. Okay.
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 Thank you.
Now that's all from my side. You can leave the call. I'll be here till 5 if you have any query. Yes.
And one more query, madam. This is again Shivanand here.
Yes.
For first week, I think it is completed, right? Assignment still we have not submitted. So can you submit now?
Assignment you can submit till 9. I think 9 is due date.
Due date. Okay.
Yeah.
Thank you.
Before due date you have to submit.
Okay, madam. Okay.
Yes, Rafi. You have any query?
Yeah, hi Alka. This is Rafi here.
Yes.
So first of all, thanks for this very good session. Just have a query on whether you will be sharing the presentation alone or this whole conversation.
Yeah, the conversation will be shared on YouTube and YouTube link as well as the presentation. Presentation will be shared with Google folder. I think they will be shared by NPTEL. They will share with you. There'll be a, I think, they'll share you within 3 days, I think.
Yeah, that will be through our registered email ID, right?
On email ID, I think there is some public sheet where you can access these, like for this session recording as well as the presentation.
Yeah.
If it's not,
Thanks.
then in next presentation you can share the email. I'll send you that.
Yeah,
If
sure,
they
Alka.
don't share
Thanks.
it, okay.
Yeah, sure.
Yeah.
Thanks, Alka. Like new for this online platform, so just a bit curiosity on this.
Okay,
Thanks.
you're welcome.